As you've probably seen from the thumbnail, this integral really doesn't make much sense, but there are specific reasons for why I wrote that. To explain the O over H part, I can draw a right angle triangle with an angle x, and labeling the opposite side as O and the hypotenuse as H. Sine of x is defined as the opposite over hypotenuse, so O over H is really just sine of x. So for the c over 2r part, I'm drawing a circle with a circumference c and a radius r. So c over 2r is really just the circumference over the diameter, which is just pi. So really the integral is quite a famous one. After all of that, the integral just reduces to the integral from negative infinity to infinity of sine x over x, and that's equal to pi, which I'm now going to prove using the Feynman trick. Here I'm just writing the integral, and since the function we're integrating, sine of x over x, is symmetrical about the y-axis, we can really write it as 2 times the integral from 0 to infinity of sine of x over x. Defining that function as j, we can say that I equals 2j. Feynman's trick is used when normal techniques like u sub and integration by parts can't be easily used within a function, within an integral. So instead we define a function in terms of alpha, and then we differentiate that, which we then integrate and get a family of functions. So then if we put a specific value for alpha into the integral, we'll return the original integral, which will then give us an easier way to get the answer. It's going to make a lot more sense when I actually do it. Here I'm defining f of alpha as e to the negative alpha x times the original function. I then differentiate it with respect to alpha, not x. I differentiate it with respect to alpha, because now, upon differentiation, I will get negative x times e to the negative alpha x multiplied by sine of x over x. And then the x's will cancel out, giving us a much easier integral to deal with. Over here, I'm just rewriting my integral with the cancelled out x's, and what I end up with is negative e to the negative alpha x times sine x. And here I can use integration by parts. So I would set my u equal to negative e to the negative alpha x, and since I'm differentiating with respect to x, my du is alpha e to the negative alpha x, and my dv is sine x, which integrates to negative cosine of x. The way I remember integration by parts is ultraviolet voodoo, uv minus the integral of v du. So I'm just rewriting that, and since I have a definite integral, I have to do it in my bounds between 0 and infinity. So I get so from integration by parts, I get e to the negative alpha x times cosine of x evaluated from 0 to infinity plus the integral from 0 to infinity of alpha e to the negative alpha x times cosine of x. And since I have another integral, which is now in terms of cosine, I will use integration by parts again to hopefully get something nice. This evaluates to 0 minus 1 since e to the negative alpha x, and we're subbing in infinity for alpha, it's going to turn out 0. And now using integration by parts once again, I'm saying my u equal to alpha e to the negative alpha x, and my du will therefore be negative alpha squared e to the negative alpha x, and my dv is going to be cosine of x, which integrates to sine of x. Doing integration by parts once again, I will multiply u times v, which will be alpha e to the negative alpha x times sine of x, evaluated from 0 to infinity, minus the integral of v du, which is going to be sine x times negative alpha squared e to the negative alpha x, and I can replace the minus sign with a plus, since the minus from inside the integral and outside will make a plus. Evaluating alpha e to the negative alpha x times sine of x from 0 to infinity will give us 0, and taking alpha squared outside of the integral, that is simply the original f prime of alpha multiplied by minus 1. So I can write f prime of alpha plus alpha squared times f prime of alpha equals minus 1. And factoring out f prime of alpha, we get f prime of alpha equals minus 1 all over alpha squared plus 1. Since we now have our f prime of alpha only in terms of alpha, we can integrate that to get our original f of alpha back. So integrating f prime of alpha, we get f of alpha, and integral reduces to negative arctan of alpha plus c. Putting the old integral back in, we have the integral from 0 to infinity of e to the negative alpha x times sine x over x dx, which we now can see is equal to negative arctan x plus c. But since we have a plus c and we don't know the value of it, we need to find the value of it. So if I take the limit as alpha approaches infinity, plugging in alpha into the left-hand side, we just get 0, and plugging in alpha to the right-hand side plugging in infinity to the right-hand side, as arctan alpha approaches infinity, the graph approaches pi on 2. So we have 0 equals minus pi on 2 plus c, which therefore implies that c equals pi on 2. So we can now write the integral as the integral from 0 to infinity of e to the negative alpha x sine x over x dx equals to negative arctan alpha plus pi on 2. Now if I plug alpha equals to 0 back into my integral, I will simply just get my original integral of j. So I will get j, or the integral from 0 to infinity of sine x over x equals to negative arctan of 0 plus pi on 2. Arctan of 0 is simply 0. So we get that the integral from 0 to infinity of sine of x is equal to pi on 2. Now writing j equals pi on 2, I said earlier that I, which is the integral from negative infinity to infinity of sine x over x, that's equal to 2j, so therefore it implies that I is simply equal to pi.